Okay, so we just did that basic concepts dealing with quadrants, and we dealt with the Pythagorean theorem and kind of introducing the distance formula. Our second set of basic concepts is dealing with domain and range and set notation. Now, this is important because, like all functions, sine and cosine and all those trig functions that we're going to deal with really soon, have a certain set of domain and range, and we need to deal with those and manipulate them in order to understand them a little bit. But before we get to that point to actually deal with like sine and cosine and tangent, we're going to deal with or be comfortable with just basic functions and basic representations for those. So the first thing that we have is defining what a set notation is. Now, set notation is just a way to describe what is included in some set of numbers by using inequalities. Inequalities allow us to decide if we have all values that are less than a particular number or greater than a particular number. And it encompasses all of those things without having to list out every number that would be involved. So it would take forever to list out the numbers between -10 and 10, because not only do you have those integer numbers, but you also have all those decimal representations like -9.9999999 and forever. So it'd be literally impossible to do that, so we represent it with some sort of inequality, or sometimes we use equations. Equations also help us, define some set of values. We use set notation by using, just so you know, curly brackets. That means that they're in that set in no particular order. That's one way to describe a set of numbers, a set of values. The other way is to use interval notations, and interval notations are used by hard brackets and parentheses. So we use we do that because we have some particular boundaries that we're setting. And we use those in like a list of numbers that actually defines in some logical sense. Versus set, it means the order doesn't matter in that set. So if I was describing all the numbers from -10 to 10, I could say 5 is in that range, but I could have put it before the -10. But in our interval notation, we define it with those boundaries so that we have a numerical sense of the order of those things. We use parentheses to exclude, and we use our brackets to include those particular numbers. And again, what I'm saying about all this stuff is not necessarily things that you need to repeat or know. I just wanted to give you some background of why we have these different representations for them. Sometimes, though, we don't have a number that is all the way down on, all the way to the left. We have numbers that are below that, or it goes off to infinity. So we use like this infinity here to describe a positive infinity, that it's going, the numbers are getting bigger and bigger and bigger without a bound, and negative infinity, they're getting smaller and smaller and smaller without a bound. Infinities always use parentheses. And the reason for that is that infinity is not a number, so there's no way to include infinity in our answer. It is a concept. It's not a particular, 10,387,000 number. We want to say that it's going off to infinity, and so we use our parentheses to bound it that way. Okay, so for this front page here, we're just going to practice going between all the different forms or all the different ways to represent our set of values. So we have graphically, which is on a number line. We have interval notation, which is using those parentheses and those brackets to describe the set. And then we also have set notation, which use some sort of inequality or equation to represent the set of values that satisfy. So I think it's easier to always start with graphically. So we're going to take this set of values and we're going to create a number line that represents that. Okay, so important values that are on our number line are the values that we see in our set. So 1, we're going to put somewhere on our number line. And I don't care if you actually use your tick marks. I just want to have 1 on there somewhere. It doesn't have to be like to scale or anything. And our set of values is saying that x is greater than 1. So we have a couple different questions. The first question is, what are the important boundaries that we have? 1 is an important boundary. We know that. 2, the second question that we ask is, are we including this value or excluding this value in our set? Now, x being greater than 1 means that this is in excluding. So for example, 1 would not be greater than 1. So it's not included in our set. Since it's not included in our set, when we use it graphically, we can either use closed or open circles, or in the book, for some reason, uses hard or soft brackets, which actually helps with our interval notation. So I'm going to use the soft or hard brackets, but know that the closed or open circles mean the same thing. If I'm excluding this value, that means that I'm going to use a soft bracket. So I'm using a soft bracket to describe that 1 is not included, it's excluded, and we're looking at the values where x is greater than 1. So 2, 8, 12, 5 million, those are all values that would satisfy that set, that would make this inequality true. Those are all values that are to the right. So we'd be pointing our arrow to the right. So if we were pointing the arrow to the left, if this were flipped around, I would use the soft bracket this way. I just knew that the answer was to the right, so I already made my soft bracket go that way. And then interval notation, it's kind of easy now to go from graphical to interval because since we're actually using the soft bracket. So we definitely have a soft bracket at 1. That's our leftmost point. We always go smaller to larger. And we're including all values that are bigger than that. So again, 2, 8, 5 million, 18 billion, all those numbers are bigger than x, this value, or bigger than 1. And that means that our endpoint, we don't have a bound on the right-hand side. It's just shooting off to infinity, and we always use parentheses to describe that. Again, for the next one, since we're given the interval notation, I think it's always easiest to do the graphical, so we're going to do that first. So we have this interval. We want to include all numbers that are from negative infinity to 4. So again, the first question that we ask is, what is our important boundaries? So obviously negative infinity is some bound to the left, meaning our arrow, when we draw this, will go off to the left. And 4 is an important bound. So I need 4 to be on my number line somewhere. So I'm just going to put it there. And again, this hard bracket means it's included, so we could use like a closed circle on our number line, but the book uses a bracket, so I'm going to use a bracket. And we want all numbers that are less than 4. So 0, negative 10, negative 10 billion, all those numbers are less than 4, so we're going to use our arrow off to the left. And then our set notation, we want to use an inequality to describe that. So again, we have an important boundary here. We have 4. That's what we're comparing all numbers to. So I'm just going to put that there, 4. And we want to include numbers that are what? We want to include numbers that are less than 4. So when we write our inequality, we have x is less than 4, and then our question becomes, do we include it or exclude it? This thing is included, so we put a or equal to underneath our inequality to describe that it's that value or equal to. Okay, next one. So this one we have 2 important boundaries. We have -6 and we have 5 for those important things that we know need to appear in our interval notation and our set. So I'm going to go interval notation first. We want this is really what we're including, all numbers that are between -6 and 5, so 0, 1, -1.2, -3.86, 5, 12, 1, 2, all those numbers would be included, so we need to include some sort of interval that would satisfy that whole thing. So our leftmost point is -6, and since our number line actually has this, it has in a closed bracket, meaning it's included. We're going to use a closed bracket for our interval notation. And then we go up to our right endpoint, which is at 5. And again, you can kind of see it in our picture. It's an open bracket, meaning it's excluded in our set. For our set notation, it's a little bit more complicated to describe this because we have two of these boundaries happening. The first part is that we want to include values that are bigger to the right than -6. So one way you could say this is that we want x values that are bigger than, and this is included, so bigger than or equal to -6. But it's not all those values because at some point we stop, right? We can't just have this arrow go on and on forever. We also need this other endpoint to contribute. So we'd say, and we need something else. We need values that would be what, less than, and this is excluded, so we're going to use just strictly less than 5. So all values that satisfied both of those inequalities. Now, since we're using both things, what that's called is a compound statement. So we're going to use them in two different ways. This is a compound inequality, but we're going to use a compound statement for our interval notation for our example 4 here. Another way to describe this, maybe like an easier way to describe this, is that since we are including things that are in between these two values, we want x to lie in between our two endpoints. So we could put just x right in the middle, and we could say that we want values that are less than 5 on this side, and we want values that are bigger than 6 on the other side. So that's another way to describe bigger than or equal to, another way to describe that same set. Okay. Last part here, again, I think it's easiest to do the graphical, so we're going to start there. Again, we have two different points of interest on our boundaries. We have -4 and we have 7, so I'm going to put them somewhere on my number line. There we go. And we're going to describe this graphically. The first thing we're looking at is that we're included, so whatever way we point our arrow, we're going to use some sort of hard bracket for the -4, and then we're going to use a soft bracket, a parentheses, for the 7. Okay, so let's look at this one. We want -4. -4 is greater than or equal to x. So this really means, I'm going to flip it around, the inequality is pointing towards the -4, so I want to keep it that way. This means that x has to be less than or equal to -4. That's the identical inequality by just flipping that, flipping where the variable is located. So x is less than or equal to -4, so we're including -4, and x is less than, so we're going to the left. In our second one, x is greater than 7, so 8, 12, 5 billion, those are all values that would be included. So I would use an open bracket and I'd be going to the right. If you're not sure, again, an easy way to tell is to pick something that would be on this number line somewhere and see if it actually satisfies your inequality. So way down here, maybe 10 is down here on my number line. Is 10 greater than 7? Yes, so we pointed our arrow the right way. For our interval, it's a little bit harder to decide. We have two different things that are acting on this. So the first one is kind of like this one up here. So we're using kind of the same idea. We are taking this this inequality that we have, this graphical representation, all the way to the left, meaning our left endpoint that we have is -infinity, and we are going up to +4 with an included hard bracket. That would be this set, but we don't want just that. Right now that would look like this, except with just like a negative here, it would be that part. So we have a secondary section here that we need to include too. And that one was more like example 1, where we have this soft bracket that goes off to infinity to the right. So we also need 7 to infinity soft bracket. And to symbolize that we are putting these two together, that they're both satisfied on this one, we use what's called a U here. This means union. And it just means it joins the two statements together. So this is also like a compound statement where we have two forces kind of acting on this one inequality. Okay, so that's like part 1 to our basic concepts for today. Part 2 is looking at domain and range, which you talked about a lot in Algebra 2 and in Algebra 1. Every relation that we have, which is just the set, any sort of set of points. So we had those set notation, which we describe those set of points. We can describe the set of points in any like graphical representation and a two-dimensional thing by looking at domain and range. And we're mostly going to be describing these relations, these domains and range, using interval notation because it's most widely used. Domain is the set of all the x values. It's all the values that are going into the function, and the range is all the set of y values. So all the y values getting popped back out. Domain, since we use, or specifically why it's a set of x values being put in, is because every function that we deal with, or most functions that we deal with in this class, and the most common ones are functions that are of x, meaning that our x is our independent variable and our y is our dependent variable. So all the values that we're putting in are our independent variable, which in all of our cases are going to be x in this class. So we'll just look at this graphical representation and come up with, and we're going to do this a million times today, come up with the domain and range for this function, or for this relation, excuse me. It is a function, but we don't know that yet, for this relation. So the way to do this is kind of a number line acting in two different ways. So we've got a number line this way, and then if you turn your paper, you can imagine a number line going this way. That's kind of our big idea here for our Cartesian plane, is that we have a number line for our x values, so that's our domain, and we have a number line for our y values, which is our range. So we're coming up with like two forces basically acting on this. So the first thing that we have is our domain. Now I want you to think about, just like we did before, if this were some number line, we have to look at our boundaries. We've got two boundaries. We have these 2 points, and both of those are closed circles, meaning they're included values. For our domain, since we're going from least to greatest for our interval notation, for our domain, when we come up with, I'm just going to use soft brackets right now, but it could be hard brackets. This point is going to be always the most left value that you see. How far left does your range go? And it doesn't have to be a boundary necessarily, like it doesn't have to end there, but it has to like reach that point. And then for your upper bound, it would be the most right point. For your range, kind of a similar idea, since range is acting as your y value instead of left and right, which x values only go left and right, that's what our x-axis does. Range for our y values, our y value axis goes up and down. So this would be the lowest point that you see, lowest value, and this would be the highest. How high, how tall does your function reach? Okay, so let's look at what that looks like. For our domain, we have this point here. That's going to be the farthest left that we're reaching. And so that lines up at an x value of -2. Oops. Now again, both these are closed circles, so we're going to use hard brackets to describe them. So we line up here at -2, and then we go, our function does whatever. In this case, it's just a straight line, and it ends up here at an x value of 3. For our range, we're looking at our lowest point first. So our relation that we have dips down to whatever this value is, which ends up being -3. And again, it's hard bracket. And it reaches up to the highest point that we see, or the highest value that it goes to is +4. And again, that is included. So sometimes we have, for like our next little section here, sometimes we have function or relations that are specific. They're a specific type of relation, and most of what we deal with are relations that are functions. Now, functions, definition of a function is that means that for every x values, there's at most one y value. So we can't have 2 y values associated with an x value. Now that might sound a little bit confusing, but there's an easy graphical way to just decide whether we have 2 x values or 2 y values that are associated with a single x value, and that's the vertical line test. So if we draw a vertical line everywhere on our graphical representation of our relation, and we hit more, it passes through that relation more than once, then that relation is not a function. So we have to make it pass the vertical line test. Now vertical lines really just represent, again, an x value. So like if I drew a vertical line on this graph up here at 1, this would be the vertical line x equals 1. So I'm looking for all of the points that cross, or where my graph crosses that line. And that would cross at this point right here. So it only would cross one time. So that's what we're looking at for our vertical line test. So I could draw something that's not a function, like this. That's something that's not a function because if I draw my vertical line here, for example, I hit 3 different times. But if I draw it here, I only hit once. It just has to happen anywhere on our diagram. So I'm going to draw one that's, this is, I guess, 7a. I'm going to draw 7b, draw a function, just so that we can see the difference. So if I draw a function somewhere on my graph, I could draw something that looks like this. So if I draw all my vertical lines throughout my entire graph, I won't hit it more than one time. Okay, last little bit here is we're going to go through just this example, but just a little bit more complicated. We're going to look at 4, and for each one, so I'm going to write this out, I'm going to find the domain, the range, and I'm going to ask myself, is it a function? And for this last one, I'm going to write it down below for that part. So the first one's really similar to our example 6. We have 2 obvious boundary points. We don't have any arrows. So these arrows mean that we are extending in that direction forever. Arrows mean that we're going to use an infinity in our boundary sets, versus these are actual points that will just have just intervals, just like we did in example 6. So our domain again are x values, which are our most left point to most right point. So our most left point is this open circle that we have, which is at -3. Since it's an open circle, so I know that's going to be included, since it's an open circle, that means that that value is excluded. It's not included in our set, so we're going to use a parentheses to describe that. And then we go along our function, or our relation. We don't know if it's a function yet. We haven't answered that question. And we hit this point over here. We go all the way to the right, which is at 2. And this is a closed circle, so we include our 2 value with a bracket. For our range, same question. We're looking at this number line here. We're deciding what's our lowest point. So our lowest point here is actually the point all the way to the right. So that happens at -1, and -1 again is included since it's a closed circle. And our highest point that we're looking at is this point right here, which lines up with our y value of 1, 2, 3, 4. And this 4 value here is open. Now it's a little bit weird because this value, like both our endpoints, our graphs, sorry, you can't see that. Both of our graphs ended here at 3, 4, and those were both our endpoints in the same one, and this one didn't. This point here at 2, 1 is like the 2, -1 is the endpoint here, and then the start of the endpoint on the other one. And that's fine. It doesn't matter that way. We just want to make sure that all of our interval notation is expressed in lowest to highest. So we don't want to flip this around and have it go from 4 to -1 because that doesn't make sense. We want it to go in a numerical sense. So I'm actually going to have you, we have to answer the question if it's a function or not. So is it a function? We have to decide if I draw all my vertical lines, will I at all at any point hit my graph in 2 places? Does it double back on itself? And the answer is no. So since it doesn't, it passes the vertical line test, meaning yes, it is a function. So I want you to actually pause the video right now, and I want you to try example 9, and you can try example 10 too, and then we'll go through those together so that you can make sure that you got the right answers. So take a second, pause it, Try example 9 and 10. Okay, you should have tried examples 9 and 10. Again, example 9 is really similar to example 8. We have some stuff that's happening on the inside, but it's primarily the same example. We are looking at our domain, which this is the most left endpoint that we have, which is at -3. And since it's an open circle, we're going to use a parentheses. I'm going to go through this one a little bit faster. Our rightmost point over here ends at 2, and it's included, so we're going to use a hard bracket. Our range, our lowest endpoint is down here, our lowest point. So that's at -1. It's included, so it's a closed circle. And it goes up to the highest point that we have is at 1, 2, 3, 4. And that one's excluded. This one, since if I draw my vertical lines, it doesn't hit more than once, it passes a vertical line test, so it should be a function. 10 is a little bit more tricky because we have this arrow that's involved, and this arrow means that we're going to use an infinity. So again, our domain, we're looking at the most left endpoint. So as we go around our graph, we stop at this particular point. So that is going to be our left endpoint, our boundary for our domain, which happens at -2, and it's included because it is a closed circle. And as we go along our graph, we end up going down here, but this down arrow is not just going down, it's actually going to the right. Slowly, but it's still going that way. So we don't have some endpoint for x values. It's going to continue on in this direction forever. So our endpoint that we have for our domain is infinity, and we're going to use an excluded because we always use excluded or soft parentheses for our infinities. Range is something similar, so we are looking for our lowest point. Well, we have this arrow, it's going down to forever, so our lowest endpoint is actually going to be -infinity since we're going down in that direction. And then our highest point, that's the easiest one to tell, is an actual point on our graph, which happens at 3. And that one's included. And this, again, should pass the vertical line test, so it should be a function. No point does it like double back on itself. This next one is trickier yet. When we look at our domain and range, we actually have these two different arrows that are involved, which means that we're going to have infinities. Domain is, again, it's a little bit tricky when we're looking at this one because we have like these two disjointed sections. So whenever we have two disjointed sections like this, that means that we're probably going to have to use more than one interval to express this. So in fact, when we do our domain, we're going to use two intervals. One is going to describe this section, and then we stop, and we have this whole entire hole in the graph where we don't have any x values that are present, and then we start back up at this value when we continue on with this section of the graph. So we're using two different intervals to describe that. So let's start with this side. If we're looking at our farthest left point that we have, since this goes up and to the left, it's going to go on to the left forever, and it'll continue on in this direction. So we start at our endpoint of -infinity for our x values. So we're starting over here at -infinity, we're following this graph down, we hit this point, and then we continue back to -infinity. So this is the most, again, we're kind of handling this in sections since we have to pick our pencil up and go back over here. This is the most left or most right endpoint that we have for this section of the graph. So it hits here at 1, 2, 3, and it's included. It doesn't have a circle, but if it was excluded, we would have seen an open circle there. And then we start up again. So ignore that section. The most left endpoint that we have in this section of the graph, the most left that we go is right here. We're continuing on going right forever. So we're going to go off to infinity in this direction, but our most left endpoint is going to be at 1. So right at the front, since we have two different ones that we're doing, we're going to use this union. So union, and we start up again at 1, and then we're going off to infinity. For our range, so that's just our x values that are kind of disjointed. It's kind of weird when we actually look at our range. So if we imagine this flipped and we look at this as our xy or our y-axis, both of these continue on, even though they're disjointed in this way, they continue on in this x-axis that we have, which is actually our y-axis. This number line is extended forever. So there are no like open holes in the graph for our range values. There's no y values that aren't present. We have an arrow that goes up to infinity, we have an arrow that goes down to infinity, and there's no points. There's a y value that's on our graph for every one of those. So our range would be negative infinity to positive infinity. And again, I know it's a little bit confusing to see the difference. One way to tell, oops, I missed a negative here. Well, correct that for me. One way to tell is if you pick a value that your interval doesn't include. So 0, for example, x equals 0 is not included in this graph. So if I go to x equals 0, I don't have any graph for that. There's no line, there's no relation there. If I pick like -1, same thing. There's no relation. If I draw my vertical line, I'm not going to hit any part of my relation. So it has to be excluded from our domain. However, if I pick any y value that I want, 10, 12, 1, 0, if I draw a horizontal line for that, I will hit the relation at some point. So that's another good way to test to decide if you did your interval correctly. Our function, if I'm drawing all my vertical lines, and here I don't have any graph, here, this point here, I'll cross it one time, and then if I keep drawing up, I'm hitting a vertical line, or my vertical line is hitting that relation in 2 spots, so it is definitely not a function. Okay, so again, big ideas here is that our domain are all of our x values, and we describe them as some interval of points. Our range is all of our y values, and again, we describe it as some interval of points. And we have definitely different representations for that. We have set notation, we have a graphical notation, we've got our number line, which is really just a one-dimensional graphical notation for that. And we can use all those different ones to describe that set of points.